once again, with candy canes and silver lanes that glow. It's beginning to look a lot like Christmas. Toys in every store, but the prettiest sight to see is the holly that will be on your own.
Oh, welcome back. This is our fourth video, I believe, on our sequence and series chapter, and a good friend of ours here tonight, Mr. Blue Blade, joining us. Don't like to brag too much, but some people have told me I sound a little bit like him once in a while. But today we have a monster test, and we're going to jump into the comparison test. But just a real quick recap of where we've been. First of all, we've learned about three specific types of series. The most famous one was that geometric series. Then we talked about a telescopic series, and those two were special because those were the only two where we actually were able to find the sum of the series besides just saying it converged. The third special type of series was a P series, and then after joining those three guys were two special tests we had. The first special test is the most popular, and that's your nth term test for divergence. And then the other one was the integral test that works really handily as long as it's a friendly series that cooperates. Oops, I should say test. Yeah, the integral test. Okay, so joining those five is going to be the comparison test. And a couple of comments that I like to make here. It says, well, so basically for those five convergence tests we've talked about so far, they work really good as long as they're fairly simple. However, we just have to tweak them slightly to make them uncooperative, and all of a sudden these tests can't be applied. So basically, like we said, a slight deviation, just a slight tweak, makes our test non-applicable. But picturing, I want to try to give you the big idea here today. Let's say that this circle represents all the series that have ever been created. You know, any series that's ever existed in the world of math. At this moment right now, we know how to handle or test the convergence of probably that many. The good news is, by the end of today's lesson, by understanding the comparison test, we'll probably be able to handle this many series. So we're really going to expand our knowledge of series and our ability to test whether they converge or diverge by the end of today's lesson. Okay, I want to go over some real quick examples that kind of paint the picture of what's easy and what's not so easy. So going into today, if I gave you something like 1 over 2 to the nth power, you said, oh, piece of cake, geometric series, R value of 1/2. Oh man, it doesn't get any easier than that. But all of a sudden, if I throw an n in the numerator, so it's n divided by 2 to the nth power, all of a sudden we just tweaked it slightly and it became, it's no longer a geometric series, it's no longer something that I can handle. Another similar example, if I said 1 over n cubed, oh, piece of cake, that's a p series, p value of 3, it converges, slam dunk, right? Well, all of a sudden, let's say we went down into that denominator and we just said, you know what, n cubed plus 1. That's all we did. We just tweaked it a little bit. We throw plus 1 in there. Now it's not a p-series and we can't handle it. Let's say we said n divided by the quantity, n squared plus 3 squared. Okay? Hey, it looks a little intimidating at first, but I think the integral test really bails us out on that one and makes it pretty easy. Now, what if I just tweak my numerator a little bit and change my numerator to an n squared and then leave the denominator exactly as is? Now all of a sudden it became rather impossible. The integral test doesn't work anymore. So we're comparing easy to not so easy, and it doesn't take much tweaking to make it a rather difficult series. Okay, we're going to jump into theorem 9.12 here, called the direct comparison test, or usually we don't throw in the word direct. A lot of times we just call it simply the comparison test. So the word direct's not really a big deal. The first thing though, let's start off by saying let b sub n always be greater than or equal to a sub n, who he himself is greater than 0. So they're both positive, and b is guaranteed to be at least as big as a, usually bigger. Now, with that given condition, we've got two statements to write down, and they're a little bit overwhelming at first, but I think we can sort them out. This first thing says, if the series with b sub n, and we'll just say generically it starts at 1 and goes to infinity. If the bigger series converges, then what do we now know for sure? Then the series with the smaller terms is also guaranteed to converge. Okay? And basically, paraphrasing that, we say if the larger converges, then the smaller one converges. See if we can, hopefully you can read that. It's getting a little messy. Okay, now we're going to twist that one completely around, okay, and they'll change colors just for fun. Let's say if the smaller one, okay, the series with the A values, the A terms. Now if the smaller ones diverge, what then has to be true? We could then say that the larger series with the B sub n terms also diverges, okay? Paraphrasing that into English, we'll just say if the smaller diverges, then the larger one also has to diverge, for sure. Okay, and I actually think there's a lot of common sense tied into these two statements. Now, there's two monster bear traps we have to watch out for, okay, that are not included in this theorem, and they're kind of misleading. And the first one says, well, what if you proved, okay, what if you proved that the smaller one converges, okay? Have you proven or told me anything about the bigger series? Okay, we absolutely know nothing about the bigger series. We'll say it's inconclusive, okay? If you prove the smaller one converges, we don't know whether the bigger one converges or not. It's inconclusive. And if we twist that around, if you prove to me that the bigger one diverges, okay, again, in this case, you've proven nothing about the smaller one. That's also inconclusive. So those are the two monster bear traps to watch out for. We got to make sure we're sticking with what the theorem says. We're going to spend quite a bit of time talking about the theory behind this theorem before we jump into some specific examples. And right off the bat, I've said, what's the big advantage of the comparison test? It allows us to compare a series with complicated terms, okay, with a simpler series. And here's the key, whose convergence or divergence is already known. And that's the key. We're comparing it to something we already know. For instance, now we already said that B sub n is going to be greater than or equal to A sub n, which is greater than 0. And that's just assumed on all of these problems. So basically we're saying each corresponding B term is bigger than its corresponding A term. B sub 1 is greater than or equal to A sub 1. B sub 2 is greater than or equal to A sub 2. And we could continue this pattern. B sub 3 has got to be bigger than or equal to A sub 3. Whoops. Okay, so forth and so forth. So basically, and I think this graph does a good job of explaining it, if we add up all of these terms and we find out that they do converge, then all of this, the sum of all these smaller ones, then naturally, and I think our common sense leads us to this fact, also converges. So here's a graph. There's just a little bit of daylight between B sub n and A sub n, and you can clearly see that each corresponding B element is bigger than his corresponding A element, and certainly if B converges, A converges. The most challenging part of today, by a mile, is being able to picking what series we're going to compare the given series to. The book's going to throw a series at us, and we've got to decide on our own what to compare it to. And picking that series for comparison is an art in itself. It is not an exact science, okay? In fact, the series you pick for comparison and the one I pick won't always necessarily be the same, and we could both be correct. But a lot of times we will be the same. Picking the right series for comparison, or picking the easiest, most convenient one, is something that comes with practice. It's a lot like when we first started U-sub. We were good at U-sub as long as we, picked the right U, and just to get in the habit of picking the right U took some time. It took a lot of practice. One of the things I want to talk about is just, how do I compare fractions to each other? What if I had 1 over 4 to the n versus 1 over 4 to the n plus 2? Okay, and I want to know who's bigger than the other one. And there's kind of an inverse relationship here. If this fraction on the right has the bigger denominator, then that means the fraction on the left is actually bigger. And we'll throw a greater than sign in here. Okay, did you catch that? The bigger the denominator, okay, the smaller that fraction becomes. Let me pick another one that's kind of convenient. Well, this time we'll contrast the numerators. If I had 1 over 4 to the n, and then over here I had n over 4 to the n, in this situation, the numerator on the right side is bigger. Then what that does is that makes that fraction as a whole bigger, and I would say I would put this kind of inequality symbol in there to represent the relationship. So let's kind of summarize what we've just said here. Let's see, bigger denominator implies that we have a smaller fraction as a whole entity. Okay. On the flip side, if we have that bigger numerator, that implies that we now have a bigger fraction. And that's going to help alleviate a lot of headaches if we stick to this simple recipe right here, is determining who's bigger and who's smaller. Okay, one last major comment before we jump into our first example. Most of the time, a majority of the time, we are going to be picking either a very basic geometric or harmonic, or if not a harmonic, a more general p-series to compare to. Okay, those are the real friendly ones that we have the most confidence in. So a lot of times if you're staring at a series and you're like, man, what in the world do I compare this to? Try comparing it to the harmonic or a more general p-series, or pick a geometric series to compare it to. Okay, here's our very first example, and I'm telling you what, don't put a ton of pressure on yourself here tonight. I think the comparison test is very difficult at first until you get lots of practice under your belt. Hopefully, we're going to spend 2 days on this, and hopefully by the end of the second day, our confidence will have built by then. But I don't want you to panic or put a lot of pressure on yourself tonight. Just do the best you can. So as you're staring at the series and you're wondering, what in God's green earth am I going to compare it to? It kind of feels like a geometric series, especially if you tried to, maybe cover up this 2 right here. Pretend that 2 is not there. If that 2 wasn't there, it would definitely be a geometric. So what I'm going to do is I'm going to try comparing it to a geometric that I know and love as such. Now I have to decide who's bigger than the other one. Okay, what you'll notice is the one on the left has the bigger denominator because of the +2, which means the one on the right is actually a bigger fraction. So here we go. In other words, this is like your b sub n, and the one on the left is like your a sub n. And in this case, we're going to try to prove that the bigger one converges, and if we can prove that the bigger one converges, then we know for a fact that the smaller one converges. However, watch out for the bear trap. If we end up proving that B diverges, then we have proven nothing about the original one, the a sub n one. So here it goes. What do we know about that first one? Well, it could be rewritten as 1/3 to the nth power. That's equivalent here from blue to green. That means your R value is 1/3. That's smaller than 1. And because your common ratio is smaller than 1, this one converges. And anytime your bigger one converges, we could say then with confidence that the smaller series also converges. Okay, here's our second example. We survived the first one. It wasn't too bad. And again, you're sitting there wondering, what in the world do I compare this rascal to? Well, I want you to, again, pretend that that +2 or the 2 plus is not there. And if that 2 wasn't there, it would really feel a lot like, yes, a p-series. In fact, what I'm going to do is I'm going to try to compare it to, and a lot of times when you're trying to figure out what to compare it to, you stick with a lot of the main components the original one has. You just kind of strip away some of the things, and all I'm going to do is I'm going to strip away the 2 plus part so that it's 1/radical n. Okay, and now we have to make the most important decision, I think, as to who's bigger. The one on the left here has the bigger denominator, so again the one on the right becomes the bigger series of bigger terms. So let's pretend this is my b sub n and the one on the left is my a sub n, or my smaller one. What we know about the one on the right, let's see, it's a p series with a p of 1/2. Uh-oh, something weird's happening here. That is smaller than or equal to 1, which means as a p-series that diverges. Remember, the p-series is kind of just the opposite of the geometric. In the geometric, we want small r values to converge in order for convergence, but in p-series, we want big p values to converge. So this one diverges. So here's the bear trap that I tried to warn you about. If you prove that the bigger series, b sub n, diverges, we have proven absolutely nothing about that smaller one. It's inconclusive. So what I've got to do is I've got to go back to the drawing board and I got to start all over. I got to maybe pick a different series for comparison. Okay, back to the drawing board. We're going to start all over. And here I'm going to show you an example of where we can get a little more creative as what we compare it to. I'm going to compare it to one of my favorite series, perhaps the most popular one of all time. I'm going to compare it to the harmonic. You're going to find out that we absolutely love the harmonic. It's just a fabulous series. What you'll notice here is that the which one's bigger? Which one's bigger? I would say the harmonic actually has the bigger denominator. Therefore, the fraction on the left side is bigger. So we got, here's my b sub n, and over here's my a sub n. So in a situation like this, we're going to try to prove that the smaller one diverges, and then we've actually got something concrete. So anyway, we know that in fact, you know what? With the harmonic, we can just refer to him by name. That is okay on the AP exam. And if we know the harmonic diverges, of course the p-value is 1 if you want to mention that. If the harmonic diverges and he's the smaller series, then the larger series is then guaranteed to also diverge according to the direct comparison test. Okay, example number 3 out of 6 total ones we're going to run through tonight. A very obnoxious looking series to start with. And again, you'll notice the index here starts at 0, and I don't want you to get too hung up on that. The only time we're even going to worry where it starts at is if we're doing a geometric and they want us to actually find the sum using that fancy formula a over 1 minus r. Other than that, we could care less whether this starts at n equals 0, n equals 2, n equals 100. We could care less. So anyway, what we're thinking here is, what if we stripped away the plus 7? What if we stripped away that part? I think we'd be staring at a p-series. So that's what I'm going to try to compare it to. Okay, I'm going to try to compare it to 1 over the square root of n to the 5th, which is also n to the 5 halves. Okay, that's what I'm going to try to compare it to. Now, as far as deciding who's bigger, you'll notice the one on the left has this plus 7 attached to it. So I'm going to make the argument that the denominator on the left is bigger, therefore the fraction as a whole on the right side is bigger. So we've got this kind of sigma. So here's my b sub n, here's my a sub n, smaller on the left, bigger on the right. I'm going to say that this bigger one, I'm going to say it's a p-series. The p-value is 5 halves. Because that's greater than 1, we could then definitely say that this rascal converges according to the p-series. And if the bigger one converges, then the smaller series is then guaranteed to converge according to, yes, the direct comparison test. Example number 4, natural log of n divided by radical n. What we want to strip away here is, if you strip away that numerator, then you're staring at a very nice p-series that diverges. And so what I'm going to do is I'm going to go ahead and I'm going to compare it to 1 over radical n. And here's a case where we're not comparing denominators, we're comparing numerators. I would say the numerator on the left here is a little bit bigger, therefore that fraction on the left is also bigger. Direct relationship between numerator and fraction, whereas there was an inverse relationship between denominator and fraction. So the bigger one, let's see, we got our bigger on the left, we got our smaller on the right. Anytime you're working with a smaller series, your only chance here is to prove that the smaller diverges. It's kind of what we're hoping for. Good news is it is a p-series. Your p-value is 1/2 because that's the exponent on n. Because that's smaller than or equal to 1, we have a divergent p-series. And anytime the smaller one diverges, we can say with 100% confidence that the larger series also diverges according to the direct comparison test. Okay, we're going to try to really challenge you here on these last 2 examples. Again, I think just deciding what to compare this ugly rascal to is the ultimate challenge. We're going to try to strip away what we think are some of the more meaningless parts. What I'm going to do is, and this just comes from experience, and once you get a couple of these under your belt, you'll be able to pull off the same tricks yourself. But I'm going to try to strip away the 3 and the plus 1, believe it or not. Again, we're going to try to strip away the 3 and the plus 1, and we'll see what happens here. We have just an n over, and I'm going to leave the denominator unchanged. And I really encourage you. You're only tweaking either the numerator or the denominator, okay? 90% of the time, you're going to leave either the numerator or the denominator completely untouched, and that's going to really help you when it comes time to decide who's bigger. You'll notice the numerator on the left certainly bigger. By the time you multiply a positive number like n by 3 and then add 1, it's bigger, therefore that fraction as a whole is bigger. So on the left side is your bigger series, on the right side is your smaller series. how are we going to prove that this one on the right side diverges? Well, we haven't used this rascal very often, but when we need them, we really need them. I'm going to go ahead, and remember this was from 1 to infinity. I'm going to go ahead and I'm going to use my integral test, okay, and I'm going to rewrite it as x over x squared plus 4. And what I'm going to do is I'm going to use a u sub here. I'm going to let u equal the denominator, x squared plus 4. My du is equal to 2 times x dx. In other words, du divided by 2x equals dx. And here's a chance if you want to try to solve this one out on your own and then hit fast forward and come see if we got the same answer. You're more than welcome to do so. I'm going to practice some good notation here. I'm going to say, okay, we've got the limit as b approaches infinity, integral from 1 to b. I've got my x over u times my du over 2x. Kill the x's, pull out the 1/2 way out in front if you want. We've got 1/2 limit as b approaches infinity. I've got my antiderivative of natural log of u. Let's see here, over from 1 to b. Scroll down just a little bit more. 1/2 limit as b approaches infinity. Just keep sticking with the good notation here. Now, as b gets really huge, the natural log graph itself gets really huge, so we'll say that has a value of infinity. As soon as you see that, you know that this integral diverges. According to the integral test, if this integral diverges, then let's see if we could scroll back up here. Then basically we're going to say that the series on the right side diverges. Then, after we use the integral test to say that the one on the right diverges, we could then say that the original one on the left side also diverges now according to the direct comparison test. So we used integral test to prove this guy diverges, and then we used comparison test to prove the one on the left diverged. So a little bit of chasing your tail, but we got there. Okay, good news is I think we got the hardest one out of the way. I'm going to try on this one. I'm going to try to strip away that +2. Always a good place to start, even if it doesn't work out. We got to try something. Sometimes you may not know if you're right or not, but you just got to get that pencil on the paper and make it start moving so that you can try something at least. So I'm going to try 7 to the n over 6 to the n. We're trying to decide who's a little bit bigger than the other guy. Again, my numerator on the left's bigger, so that fraction as a whole is bigger. This is b sub n on the left. This is a sub n on the right. I want you to feel comfortable rewriting this blue one as 7/6 to the n, okay? I want everybody to feel extremely comfortable doing that, knowing that that is a legal move. You now have a geometric series with an r value of 7/6, which is certainly greater than or equal to 1. Because of that, it diverges. And the direct comparison test says if the smaller series diverges, then the sum of the bigger series, or the terms within that series, also diverge, according to the direct comparison test. Well, ladies and gentlemen, that's day 1 of the direct comparison test. I hope you've built a little bit of confidence. We'll continue to work on this together tomorrow, and we're going to continue to sprinkle in a bunch of old ones tomorrow just to keep you on your toes and see if we can keep them sorted out. Take it easy. We'll see you tomorrow.